0. That goes away. J dot I? J dot J? 1. Which is what we had down there, equals 6. Let's look at it a different way. Because I gave it to you in rectangular coordinates. I think most people can recognize, oh, I got 2 I hats there, let's multiply those. Got the j hats, let's multiply those, let's add them. However, suppose I have A in that direction and B in that direction, and I have some angle theta between them. Again, I'm multiplying parallel parts, so I would break A up into its components. I have to figure out how much of A is in the same direction as B, how much is perpendicular to B. So this part right here, I'm just going to label A parallel, and this would be A perpendicular. If I am multiplying the parallel parts, then A dot B is going to be that parallel A times B. Well, that's a right triangle right there. My length here of my vector, A vector, is A. So what is this length right here? My hypotenuse is A. What would be this side? I saw your lips move, Osama. I just didn't hear what you said. Or are you thinking out loud?
Thinking out loud.
Okay. Flashback to trig.
Cosine.
So this would be A times the cosine of theta. This would be A times the sine of theta. So this is just A cosine of theta times B, or AB cosine theta. So if I did I hat times I hat, what's the angle between them? What's the angle between any vector and itself? What is the angle between a vector and itself?
0.
So if I did I hat dot I hat, the angle between them is 0, so cosine of 0 is times the magnitude of that times the magnitude of that, so I dot I is 1. I hat dot J hat, well, the angle is 90 degrees. Cosine of 90 degrees is
0.
and thus I dot J or J dot I, 0. And taking it one step further, any vector, dot product with itself. Again, the angle between them is 0, cosine of 0 is 1, and so this just becomes b squared. And that is what we need to know to derive the fourth one. So I say let's try to derive the fourth one, take a break. And you will feel that much more complete and that much closer to world domination. So from there and previously, I know that acceleration, oh, that's right, I really don't want to use that marker. Is v final, well, change in velocity over change in time. Because this is average velocity, but we're dealing with, again, acceleration is constant, so the average and the instantaneous are the same at all times. That's equal to Vf minus Vi over t. And I know that the displacement from the second equation over there 1/2 times VI plus VF times time. And I'm just gonna do a dot product there. I'm gonna do A dot delta X. So that's gonna be this, VF minus VI over T. Dot product, 1/2 VI plus VF times time. All right, so right off the bat, how can we simplify this?
The T's cancel.
Absolutely. The 1/2 right there can just be pulled straight out, or we can just multiply everything by 2 and get rid of it. So I'm gonna do it that way. So multiply everything by 2, so I have 2A dot delta X is equal to this dot product with that. Oh, those should be vector symbols over them. And let's just FOIL. That's gonna be equal to first, so that's VF dot VI, outer, plus VF dot VF, inner, minus VI dot VI, last, minus VI dot VF. Those are all supposed to be V's. Well, I got VF dot VI and VI dot VF. Does commutative property hold? Benjamin says yes. Feeling confident? All right, let's go with it. If you're multiplying the I hat, think in rectangular notation, if you multiply the I hats together, it doesn't matter if you do, in our example, 3 times -2 or -2 times 3, it doesn't matter the order in which you do it. Commutative property does hold for dot products. It does not hold for cross products. But for dot products it does, so what I'm left with is 2A delta X dot delta X equals, that's just VF squared minus VI squared. The dot product produces scalars, so this is not velocity squared, this is speed squared. So it simplifies it some, but you also lose some information. And so we are now left with the fourth one. I'm going to do VF squared first is equal to VI squared plus 2A dot delta X. And there you go, the big formulas. All right, I think it's time to take a break. Stretch legs, rejuvenate, get ready to rejoice when you return. All right, so let's actually use this stuff, come up with, do some number crunching. A car is initially traveling at negative 40 meters per second, which is about 85 miles an hour. But accelerating uniformly. At six meters per second squared, positive. For 11 seconds. At the end of that 11 seconds, is the velocity? What is the displacement? What is the distance? And let's just, at what time does the car stop? How far did the car travel? The initial to stopping. For the 11 seconds. What is delta x? What is the average velocity? What is the average speed? All right, so we have all the bits and pieces here. Now, there are 5 major things that we typically find in these problems. You have displacement, initial velocity, final velocity, acceleration, and time. If you know 3 of them, you can find the other 2. We're a constant acceleration problem. So, what do we know?
Initial velocity.
Which is?
Negative 40 meters per second.
Now, I did not explicitly state that that was a velocity, but the 2 clues here, 1, units of meters per second, and 2, negative. A speed will not be negative. Speed is always positive. I guess unless you go backwards in time, but we'll assume that that's not possible right now. All right, what else do we know?
Acceleration is 6
Okay,
meters per second.
thank you. And the last bit of information.
Time.
Which is?
11 seconds.
All right. We know 3 things, we can find the other 2. Now the first question is, what is the velocity at the end of that time? Now, if you're panicking, just plug those 3 things that we know into all the formulas and see which one plays out. Or you look at it, you're thinking, well, I'm trying to find this, I don't know that, so I want to get the equation that doesn't have delta x in it, which would be? So if we plug into that, we get V final is equal to negative 40 plus 6 times 11, which is 26. You don't have to put the plus sign there, but just emphasizing we are dealing with it, moving in the positive direction. Unless I made a mistake. All right, so we now know VF. How do we find displacement?
Use the second equation.
Okay. So that's average velocity times time. What is the average velocity anyway?
Negative 7 meters per second.
Absolutely. How'd you get that?
Took the initial, added it with the final, divided it by 2.
There you go. So we have my displacement is equal to my average velocity. So negative, we're going to do it that way, times 11. So negative 7 times 11. Doing that fancy math in my head. I don't have to keep track of units because I'm already dealing with meters and seconds. The SI units are nice units. And I make sure they're there at the end. Or if I'm putting it over here, I can make sure it's over here. All right, so we got the first two answered and one of the later ones answered. So, well, questions up to here? All right, so at what time does it stop? Again, as long as I know three things, I can find everything else.
At 6 2/3 seconds,
How'd you get that?
I divided the initial velocity by the acceleration.
In essence. If we think about this as a separate problem, I know that that's 0 meters per second, that's still negative 40 meters per second, that's still 6 meters per second squared. That's what we're working with, trying to find time now, using the same equation there. So I got 0 equals negative 40 plus 6 times time. Negative 40, positive 40 divided by 6. And so 6 2/3.
Yes.
Now, I do want to point out, yes, you can, I assume you didn't write anything down, you just knew how to do it.
Yeah.
If you keep track, if you plug into the formulas, an advantage of doing it that way, as opposed to just in your head, and in your head's fine if it works. If we end up with a negative time, that's a red flag that either the problem is impossible, it would have had to have taken place before the problem started, or there's a mistake somewhere. So just please be aware of that. And so how far did it travel in that 6 2/3 seconds? How would you find it?
You take the average velocity, but I don't know if that would really be accurate.
What would what average would you use?
The 7 meters, negative 7 meters per second.
Yeah, no, it's not the average for the first 6.67 seconds. That's the average over the full 11 seconds. What is the average for the first 6.67 seconds?
If final velocity is VF is 6 point whatever.
That, the time is 6.6 whatever.
Negative 20.
Yeah, how'd you get negative 20?
I did initial minus 0 because that's our new flag.
Plus 0.
Plus, excuse me.
Yeah, that's our problem right there. My average is just the average of those two numbers, so that's negative 20. So negative 20 times 6.67 using this equation, or you could have plugged in that one too. So we end up with negative 20 times 6.67, or 66, however long you want to take it. And you end up with 13.3 repeating seconds. Oh, nope. What are the units? By 133.3. What are the units?
Meters per second.
You went too far.
Meters?
Meters. Yes, how far that traveled. We'll plug it into this equation right here to find displacement, which is the length. All right. Now, the displacement is negative 133.3, but what was how far did the car travel?
It's negative 77.
No, just from the beginning of the problem to when it stopped. When the car stopped, not the problem stopped.
Like the distance.
Yeah.
Would it be 133.3?
Yes, it is. The negative is just a directional thing, the distance it actually traveled, because it doesn't change directions, it's just going in a straight line. That's the distance right there. We can't do that for the entire problem, that we have an entire displacement of negative 77 meters, but we can't just say that's the distance traveled by taking the absolute value of that, because it does change directions. So what we're working on here is, stick in my pocket. Nope. Get something with it. It will turn on. All right, so visualizing it, we'll just say to the right is positive. Doesn't really matter, just we pick a direction. So it starts out going that way. There's the starting point. It goes this way, 133.3 meters. I know that, and then it stops and starts coming back. I know that it ends up 77 meters on the negative side from where it started, because we already figured that. That's what this is. So the amount of distance it traveled back would just be the difference between these two, which is something special. 56.3. Is that right?
Yep.
All right. So the distance traveled.
Uh, 189.6 meters.
Absolutely. Yep. 189.6 meters. And so how would we find average speed?
Dividing that by time
Which time?
at the 11 seconds.
Yep. That's not an acceptable final answer, because basically only one fraction per problem, or per answer, the numeric part of the answer. So, because I've got a decimal point there and the fraction bar, I'm counting that as two fractions. So you could just do 1,896 1/100ths meters per second, that's acceptable, or actually do the division problem. Questions to hear? Yes, Jensen?
I have an off-topic question.
Okay.
Completely off-topic.